This is the beginning of Unit 6, Week 3, Lecture 6, Part 2, so the rest of Lecture 6. And so in the Part 1, we looked at what a photovoltaic cell was and just sort of the basic concept behind how an electron can move in a semiconductor, how you can motivate electrons to move in semiconductors by supplying an external energy such as heat or photons from electromagnetic radiation. And we saw that it seems pretty straightforward. So the question is, why don't we just switch to solar power? Seems like that would alleviate the problems of pollution and global warming and all the other problems associated with the current way that we power our society. Well, the deal is that as it is, there's only 1% of the power being provided by photovoltaic cells because the technology itself is still sort of expensive. Also, when I say expensive, I mean it's expensive. The silicon, again, just like hydrogen, you can't just dig a hole and dig up pure silicon crystals out of the ground. Silicon crystals are made from sand, silicon dioxide. And so there's a process of heating the sand and then cooling it back down carefully such that you align the silicon atoms in a crystal. So that's there takes energy and money. Also, the efficiency is quite low on solar cells as it is. And when we say the efficiency is low, the amount of energy coming from the sun compared to the amount of electrical energy is relatively low. Early on, the solar cells only were 4% efficient. Now the efficiency is up into the teens. And so there's a lot of research going on to try to increase the efficiency of these photovoltaic cells. And one thing is they found that you can switch from crystalline silicon to amorphous. Okay? And solids can exist as a crystalline solid where all the atoms are in it arranged neatly in a crystal, or amorphous is in a random arrangement, more like a glass would be considered an amorphous solid where the atoms aren't all lined up. Well, imagine if you're going from sand to crystalline, it's more difficult than going to sand just to an amorphous silicon. And so for the photovoltaic industry, then it's found that the amorphous silicon actually is a more efficient conductor of electricity than the crystalline. So efforts to produce amorphous silicon in the form of these photovoltaic cells is underway. Also, the other thing is multi-layer cells. Right now, I mean, the traditional photovoltaic cell is just a layer of an N-type and a P-type, and they're pretty thick. And what they found, research has found, is that if you have thinner layers of N and P-type and then multiple layers of N-type, P-type, N-type, P-type is what I mean, then you get better efficiency, better voltage, better movement of electrons and transition from photons to moving electricity. And just to give you an idea of the scale of these thin layers, it's on the scale of microns. One layer is 15 microns. A human hair is about 50 microns. So, about less than 1/4 the size, the thickness of a hair. Imagine that's some serious technology there and engineering to fabricate these photovoltaic cells. So there's an upfront cost and investment by a company to make these cells. There has to be a market. Somebody needs to want to buy them, and the only way that you're going to buy them is if there are uses for them. So you see, it's a market-driven thing, and there needs to be incentives and whatnot, and investment to bring this industry along. So because of all of this, the photocells are still more expensive than traditional methods of producing electricity. That's why less than 1% of electricity is generated using photocells. So it's clean. There's a lot of potential there. It just requires a decision by someone with money and power to decide to devote to developing this technology. And you can see this graph just gives you an idea of photovoltaic power installed in kilowatts. Germany is the leader in using photovoltaic cells. I don't know if you remember, but France was the leader with nuclear. Germany with the photovoltaic cells. Where's the US? Over here. So about 1/6 the amount of kilowatt compared to Germany, and Germany is a heck of a lot smaller of a country. And Japan is in between. So you see, it's a decision, it's sort of a national decision to invest in this type of energy. It's renewable because the sun obviously is not going to burn out anytime soon, and it's clean. So it's really a matter of this country deciding to invest in the technology, and we'll see more investments from the United States as the years go on.